Is going to fill in example 3 from the National 5 Pythagoras notes. This example is all about Pythagoras in circles, and as you can see at the beginning of this example, we have got a couple of definitions and a little bit of context for the question. Now, a special type of question occurs when we have isosceles triangles in particular inside a circle, and we may be asked to find its height. So you would tend to have a diagram, you'd be asked to find the line which goes from this straight line here up and through the circle to the top, or if the circle was round the other way, then from that line to the bottom of the circle. The straight line in the diagram here, highlighted in purple, is known as a chord, and if we can have a look at the horizontal line coming from the centre to the chord, it is going to split the chord in half. So by doing that, we have a right-angled triangle coming from the horizontal and the vertical, and then we've got a diagonal line as well. Bear in mind that this diagonal line in blue here is a radius of the circle, so if we are told at any point that the radius of the circle is a value, then we can mark on that line with that number. We also will generally be told the length of the chord, which is the full purple line, and therefore if we have half the line for a right-angled triangle, then this side of the right-angled triangle would be half of the chord length. A chord then, just for some definition, is a line which goes from one edge of the circumference to the other. It does not have to go through the centre. A diameter is a particular type of chord which does go through the centre. Any line, any straight line which goes from one edge of the circumference to the other is known as a chord. So, in example 3 then, we have a context. We've got a tabletop, which is part of a circle. Chord AB is 70 centimetres, marked on the diagram, and the radius is 40 centimetres, also marked on the diagram. The first thing I want to do is to identify the right-angled triangle, which would appear here. I'm going to draw that outside of my diagram to the side here, and you're going to mark on the right angle. I said in a previous video, if ever you are to draw out a right-angled triangle, make sure that you mark on the right angle. So therefore, on your hypotenuse, the largest side, you've got 40 centimetres. The side above one of your shorter sides is going to be half of the chord, so 35 centimetres. And my first task is going to be to find the value of side A, or one of the smaller sides, in the right-angled triangle. The reason for this is that I need to find the height of the width of the table, which is that line here. That is comprised of this line, which is part of the triangle, and then that line there from the centre to the circumference. That line, remember, is 40 centimetres, as that's also a radius of the circle. To find the side A in the triangle, I'm going to use the altered version of Pythagoras' theorem, which is the a squared, a smaller side, is c squared minus b squared, which means c is 40 and b is 35. So that will be 40 squared minus 35 squared. That gives me a value of 375. Therefore, the value in the triangle is the square root of 375, and that will give me 19.4 to 1 decimal place. If I mark that onto the diagram as 19.4, it's now more clear how we are going to find the width of this tabletop. It is the 19.4 line in addition to the 40 line below. So 40 plus 19.4 will give us 59.4 centimetres as the width of the table. So for each of these questions, you are looking to identify the right-angled triangle, to then draw the right-angled triangle at the side, or on your diagram, of course, to make sure that you mark on the right angle on the diagram. Generally, find the smaller side, but if not, find a missing side, and then complete the question, which will be different depending on the context of the question, to find your final answer. Okay, there is one more example of this in the past paper question of your notes as well, so we will see another variation of this later on.